So the next definition is Riemann integral. This is the definition that we are going to study now. Riemann integral. So till now, what were the definitions that we studied? We studied about partition, we studied about subintervals, we studied about length of subintervals, then upper Riemann sum, lower Riemann sum, upper Riemann integral, and lower Riemann integral. Now coming to the exact definition of what our chapter says. So Riemann integral. If f is bounded function, if f is a bounded function on closed interval a comma b, and if integral a bar to b f of x dx is equal to integral a to b bar f of x dx, then f is said to be Riemann integral on closed interval a comma b. What are these integral a bar to b f of x and integral a to b bar f of x? This is LF. This is UF. That is upper Riemann integral and lower Riemann integral. If those both are equal, then the integral is said to be Riemann integral. Otherwise, it is said to be normal lower Riemann or upper Riemann. Okay. There is a note point which says if f is Riemann integral, if f is Riemann integral where on closed interval a comma b, the entire chapter will be studying about closed intervals only. So that is a comma b. Then we can write f as an integral. F is R integral. F is R integral on closed interval a comma b. Or symbolically we can write f belongs to R of a comma b. I hope you know the difference between this R and this R. This is a real number R and this is the normal R. So in this chapter, this R is Riemann integral. Okay. Now let's move on to the proof. Just remember that if UP and LP are equal, that is upper Riemann integral and lower Riemann integral are equal, then that is said to be Riemann integral, and this is the symbolic form. If the function f will belong to the Riemann integral which is closed in the closed interval a comma b. Now let's look into the theorem 6, which says if f belongs to R over a comma b, that is Riemann integral of a comma b, then minus f also belongs to a comma b. And as we are talking about the integrals, you got to write that one. Integral a to b minus f of x dx is equals to minus integral a to b f of x dx. So now we have to prove this whether those both are equal or not. If they are equal, then this condition satisfies. Otherwise, we'll just see what happens. Now, like looking into the proof, given that what is that they gave, f belongs to R over a comma b, that is Riemann integral over a comma b, and integral a to b bar f of x dx is equals to integral a bar to b f of x dx. Lower Riemann and upper Riemann are equal. This is equals to, like whenever you have b bar to a bar, when they are equal, you can write it as integral a to b f of x dx. Okay. Whenever you have integrals like a to b bar to a bar to b, you can write it on the whole interval, that is integral a to b f of x dx. Now we will be defining the partition on this intervals. Let p is equals to, how will we define partition? A is equals to x naught, x1, so on up to xn is equals to b. Okay. Let this be what? Partition, where on the closed interval a comma b. On the closed interval a comma b. Now what is that they gave? They gave f belongs to R over a comma b, then minus f belongs to R over a comma b. So we have to write that. And you make sure that f is a bounded function. Like in the entire chapter, we'll be studying whenever they talk about f, that will be a bounded function. So given that f is bounded on closed interval a comma b. If f belongs to r over a comma b, minus f also belongs to r over a comma b. So if f is bounded, minus f will also be bounded on a b, right? Minus f will also be bounded on closed interval a comma b. Now, as we spoke about f and minus f, we'll be talking about m and mr's. Okay. So capital M and small m are in supremums and infimums. I'm just writing infimum and supremum of f. As we are talking about r, what is r? The rth subinterval. So of f on IR. What is IR? XR minus 1, comma XR. Am I clear? Why are we writing MRs? Because we wanted to prove it on the whole interval. Next, how will we define minus f and f? Infimum of minus f is equals to minus of supremum of f. What is minus? Minus will be like this. What is supremum? Capital MR. So infimum of minus f equals to minus capital MR. Supremum of minus f will be equals to minus infimum of f. So what is this? Minus small mr. Okay, now we'll just write up minus f. What is up minus f? You have to write up's definition. That is, we are talking about infimum now. Integral summation r equals to 1 to n minus mr delta r is equals to minus taking out, then you'll have summation r equals to 1 to n small mr into delta r. This is equals to minus, what is small mr delta r? F of p comma f. Okay. Next, LPF. LP comma f is equals to minus f. This is equals to summation r equals to 1 to n minus capital mr into delta r is equals to minus summation r equals to 1 to n capital mr into delta r. This is equals to minus UPF. Okay. Now we'll define the integral. Integral a to b bar minus f of x. So what is that we have to define? Minus f, integral minus f equals to minus integral f. Integral a to b bar minus f of x into dx is equals to, what is integral a to b bar? How will we define? What is upper? How will we define up? Integral a to b bar f of x dx is equals to, this is infimum of all the UPFs. So that is what we got to write. Infimum of all the UPF, as we are talking about minus f, such that p belongs to phi of a comma b, set of all partitions. Okay. Now in the same way, we'll be defining integral a to b bar. In place of UPF, what is that we have to substitute? Minus LPF. Okay. So integral a to b bar minus f of x into dx is equals to infimum of minus LPF such that p belongs to phi of a comma b. This is equals to, what is infimum? What is the definition of infimum? You can write it as minus supremum of LPF such that p belongs to phi of a comma b. Okay. But what is supremum of LPF? Minus integral a bar to b f of x dx. Okay, this is a definition. Let this be equation 2. Now let us define a to b or a bar to b. Let us define now. This is a to b bar, that is upper. We'll define a bar to b. A bar to b f of x dx. What is this? Obviously supremum of LPFs. This is by the definition. Supremum of LPF such that P belongs to phi of A comma B. This is equals to supremum of what is LPF? Minus UPF. Minus UPF such that B belongs to phi of A comma B. Okay. Now this is equals to supremum can be written as minus infimum. Minus infimum of UPF such that P belongs to phi of A comma B. Now what is infimum? You know, this is by the definition of integral A to B bar. So minus will be as it is. This will be integral A to B bar f of x dx. Okay. Let this be 3. So from 1 and 3, what is that we can conclude? This is A to B bar minus f of x dx is equals to minus A bar to B f of x dx. This is integral A bar to B f of x dx is equals to minus integral A bar to B f of x dx. We'll write all these clearly. So from 2 and 3, what is that you'll get? Integral A to B bar minus f of x into dx is equals to integral A bar to B minus f of x into dx is equals to minus integral A to B f of x dx. Okay. And this implies minus f belongs to R over A comma B, and integral A to B minus f of x into dx is equals to minus integral A to B f of x dx. Okay, hence proof. This is what we wanted to prove. Integral A to B minus f of x dx is equals to minus integral A to B f of x dx. Now we'll look into the next theorem, which says this Theorem 7. Total you have some 18 theorems or something. So Theorem 7. The statement says if f belongs to R over A comma B and K belongs to R. What is R? Riemann integral. Then K into F, like if a constant is multiplied into the function, will that be belong to R of A comma B? And if so, if this belongs to R, then you have to prove that A to B K f of x dx is equals to K into integral A to B f of x dx. These type of problems mostly they'll be asking you in short. Otherwise, they can ask you in long, like the entire thing, if the constant, if the addition, multiplication, division, these kind of questions all put together, they'll ask you in long. So let us quickly move into the proof. Given that, what is that they gave? F belongs to R over A comma B. Okay. And from the previous theorem, what is that we can say? Integral A to B bar f of x dx is equals to integral A bar to B f of x dx is equals to integral A to B f of x dx. Okay, this is what we can tell. Now, in case 1, I just wanted to assume that this k is greater than or equals to 0. Whatever the constant is there, I'm taking that as a positive constant or equals to 0, greater than or equals to 0. Now we have to define a partition P in such a way that x is equals to a0, a1, so on up, a is equals to x0, x1. A is equals to x0, x1, so on up to xn minus 1, comma xn is equals to some b. What is this? This is a partition. B partition on where closed interval a comma b. Okay. Therefore, f is bounded on AB. F is bounded on a comma b. This implies, now tell me, if f is bounded, whenever you multiply a constant, that is k into f, that will also be bounded. So k into f is also bounded on a comma closed interval a comma b. It is bounded. It is also bounded on the closed interval a comma b. Now we have to talk about supremums and infimums. Okay. So small mr be infimum, and then capital Mr be supremum, where of f on, as we are talking about r's, it should be on rth subinterval, that is IR, xr minus 1 comma xr. Okay. Now infimum of k into f, this is equals to k into infimum of f. I'm just taking this constant out and I'm writing infimum of f. But what is infimum? What is infimum? K into small mr. K into mr. Then supremum of k into f is equals to k into supremum of f. What is supremum? Capital Mr. So this is equals to k into capital Mr. Okay. As we are talking about r's, write on IR. That is the rth subinterval of, on the rth subinterval of IR. So u p comma k into f is equals to k into u. What is u? That is capital K into Mr. I'm just directly writing this one. This you have to write this one. Summation r equals to 1 to n. This will be k into mr. That is, we are talking about the upper. That is, what is supremum? Least upper bound. What is infimum? Greatest lower bound. So as we are talking about upper bounds, you got to write k into mr. K into mr into delta r. Okay. And this is equals to, take k out and then write r equals to 1 to n mr into delta r. What is capital Mr into delta r? K into UPF. Right? All these are from the definition. So make sure that you are perfect with the definitions. LPKF. Same thing, you got to substitute this one. Summation r equals to 1 to n k into small mr into delta r. So take k as a constant out. Summation r equals to 1 to n small mr into delta r. So that is equals to k into LPF. Okay. This is what we got after we took MR and like infimums and supremums. Now what is that we have to do is, we got to write integral a to b bar. What is that we actually have to prove? Integral a to b bar kf of x into dx equals to k into integral. That is, integral kf is equals to k into integral f. This is what we have to prove on the whole interval a comma b. So for that, I'm just taking a to b bar k into f of x into dx. Okay. To prove that one, this is equals to, what is kf into f of x dx? This is equals to infimum of, what is upper UP formula? This is integral a to b bar f of x dx. That is equals to infimums, as we are talking about UPF, infimum of all UPF. So that is what we have to write over here. Infimum of all this thing. Infimum of UPF, UP comma KF. But what is UP comma KF? You can write it as infimum of K into UPF. Okay. As this is a constant, take that one out. K into infimum of UPF. So this is equals to K into, what is infimum of UPF? Write down the definition. What is that? Integral a to b bar f of x dx. Okay. This is all from the formulas of UPF and LPF. Now we have to prove the same thing with a bar. So what is that we got? Integral a to b bar kf of x dx. We got this as k into integral a to b f of x dx. Okay. Since from 1. Actually, what is that we have to get? We have to get a to b bar. But as we have seen earlier, integral a to b bar is equals to integral a bar to b is equals to the whole integral a to b bar. So from this one, I'm just concluding it and writing it as integral a to b f of x dx. Okay. I hope you understand this one. Now we'll prove for lower integral. That is lower sum. Integral a bar to b f of x dx is equals to, sorry, it should be k. We are talking about the constant, right? So it is k f of x dx. That is equals to supremums. What is the definition of lower? A bar to b f of x dx is equals to supremums of all LPFs. So that is what we have to write. Supremum of L into P comma Kf. But as we have already proved, what is that? Supremum of K into L into Pf. We proved this one earlier. That is equals to, as K is constant, take that out. Then you'll have supremum of LPF. Right? And this is equals to K into integral A bar to b f of x dx. And from the result, what is that we can conclude? What is the result? A to b bar equals to A bar to b is equals to, it will be A to b. So this is equals to K into integral A to b f of x dx. So this be 2, this be 3. So from 1 and 3, what is that we can, sorry, from 2 and 3, what is that we can conclude? We can conclude that integral A to b bar f of x dx, it should be k, integral A to b bar k f of x dx is equals to integral A bar to b k f of x into dx is equals to integral A to b k f of x dx. Okay. So take this k outside. So this will be k into integral A to b f of x dx. So this implies k into f belongs to R over A comma b and integral A to b kf into dx of x into dx. This is equals to k into integral A to b f of x dx. When this is true only when k is greater than or equals to 0. Now what if we have k is less than 0? What should we do if we have k is less than 0? Now this is case 2. In case 2, we have what if k is less than 0, strictly less than 0. So I'm just assuming k to be some minus L, because if it is less than 0, you'll have only negative values. So k equals to minus L, where L is some positive number. Okay. So I'm just writing this as, what will kf be? K into, this will be minus L into f, right? I'm just substituting this k value. Since f belongs to R over A comma b, since f belongs to R over A comma b, this implies minus f also will belong to R comma b, R over A comma b. That is, if f is a Riemann, minus f is also Riemann. We have, what is that we have? This one, L is greater than 0. We have L is greater than 0 and minus f belongs to R over A comma b, right? By case 1, what is that we can conclude? By case 1, L into minus f belongs to R over A comma b. That is, if f belongs to R over A comma b, kf also belongs to R over A comma b. But here what is k? But what is k? K is minus L. So minus L into f also belongs to A comma b. That is what that step means. So minus L into minus f belongs to R over A comma b. So what is L into f? That is k into f belongs to R over A comma b. And then you'll have the same story. Integral A to b k into f of x dx is equals to integral A to b minus L into f of x dx. So put minus like this only and send L out. L integral A to b minus f of x dx. Okay. So write this as, just write L as L into minus 1. I'm sending minus also outside. A to be f of x dx. So this will be equals to minus L into integral A to b f of x dx. Now substitute what is that we have took in the starting? K. K into integral A to b f of x dx. That is what we want and that is what we prove. Okay.